Hello, this is Jonathan Gardner. Today we're covering section 2.6 of Surway and Jewett's Physics for Scientists and Engineers, 9th edition, which you can find available free online because of its generous copyright. So this section covers an analysis model, particles under constant acceleration. So previously we looked at an analysis model of constant velocity, right? And we also looked at what constant speed might look like. So today we're looking at constant velocity. If the acceleration of a particle varies in time, its motion can be complex and difficult to analyze. Okay? A very common and simple type of one-dimensional motion, however, is that in which the acceleration is constant. Okay? There's lots of different kinds of motion out there, and this is one kind of motion. So just because you understand this doesn't mean you understand all kinds of motion, but you do understand a good portion of motion. And hopefully what we learn from here is applicable to other kinds of motion, right? So in constant acceleration, the acceleration is always equal to the average acceleration. So what that means is the derivative with respect to the velocity, the derivative of the velocity in x with respect to time is always equal to the change over longer periods of time, right? Okay, so that is what we're talking about here. So the average acceleration is the acceleration at all times. So although this doesn't happen very often, it happens often enough that it actually creates a useful model that we can use, right? So let's just write this out this way. Acceleration in the x direction is the final velocity in the x direction minus the initial velocity in the x direction minus the final time, or final time divided by the final time minus the initial time, right? Okay, now if we take the initial time is equal to 0 and we use any other time for the final time, we'll just say that the t is the final time, right? Then we could rewrite this equation as it's the final velocity minus the initial velocity over the time or the duration of the action. And so moving some things around, we're going to multiply both sides by t. We're going to move this over there, so we get Vx in the final direction is equal to the initial velocity plus the acceleration times the duration of the time. Remember, this is only for constant acceleration. If the acceleration is changing, this equation is not valid. You can't use it. Okay? So only for constant acceleration. Let's take a look at what this looks like graphically, and they have it in the book if you want to see. Okay? The position is going to form a parabola. Okay? So this is the position, this is the time. The velocity is going to form a straight line because the change in the velocity over time, the slope of the velocity graph is always the same, doesn't change. And then finally, the acceleration is just a constant value, doesn't change. Okay, so we might say between here and here, between there and there, so we're just lining all these things up. My pen is dying, I need a new pen. Okay, so this is the initial velocity, this is the final velocity, this is the duration t, which is this whole thing here. And then we have an initial position and a final position, and the acceleration is constant at a. Okay, that's kind of what's going on here, or a sub x is the acceleration. Okay. Because velocity at constant acceleration varies linearly in time according to equation 213, we can express the average velocity in any time interval as the arithmetic mean of the initial velocity Vx and the final. So we could say the average velocity is going to be the initial velocity plus the final velocity over 2. We're taking the average of the two velocities. So we say, what's the average velocity between these 2 points? We just take the average. We look in between those 2 points. That gives us the average velocity. Okay. And again, this is only for constant acceleration. If the acceleration is not constant, then this is not necessarily true. Okay. Now, what is the position over time? Okay, so we're going to say the final position is equal to the initial position plus 1/2 the change, the average weight, 1/2 of the average velocity, okay, times t. This is the average velocity. This whole, I need another colored pen. This is the average velocity, okay. And what does that average velocity mean? You're just taking the difference in the two positions and you're finding the straight line slope, okay, of those two things, okay. And so let's do the final velocity. Let's substitute that in. The initial velocity plus, we calculate the final velocity given the initial velocity here. We can manipulate this equation around. Let's see, the final velocity is going to be equal to, here it is, the initial velocity plus ax, t, and that's times t. Okay, and then let's distribute out the t there. Okay, so we get 2 of these vxi's times 1/2, so that's just 1 vxi. And then 1/2 times at squared. And this is how the displacement happens. Okay, so that's how far the object moves in a certain amount of time, given a certain amount of acceleration, given a certain initial position, initial velocity. Okay, now those of you who know calculus say, why did you do it this way? Well, because it works. Okay. Suppose that we don't know what the acceleration is. Hold on a second. No, the curve is a parabola. The slope of the tangent line of this curve at t equals 0 equals the initial velocity, and the slope of the tangent line equals the final velocity at that time. Finally, we obtain the expression for the final velocity. That does not contain time as a variable. So let's eliminate time as a variable to calculate the final velocity. Okay, so we're going to say the final position is equal to all of this. How do they do this? They take equation 213 and plug it into 215. So we start with 213, which is this equation here. And then they plug it into 215, which is the final is equal to that plus that. Nope. This is equation that they're plugging that into. So x sub f is equal to x sub I plus 1/2 vx sub I plus vx sub I. I'm going to put a parenthesis around that, plus axt times t. Is that correct? Okay. No. No, they're substituting it in for time. Let's do it again. Sorry. And then for t, if we solve this equation for time, we get time is equal to vxf minus vxi divided by ax. Okay? Yes, that's correct. So vxf minus vxi divided by ax. So we're substituting that all in for t. Okay. And moving some things around, it's going to be a little bit complex here. So x sub I plus, we have a vxi, a minus vxi. So minus 1/2 vxi over ax. Let's just leave that all over ax. Let's leave that a plus. This is a minus squared. We have vxf squared. And then we have the cross term which cancels. Okay. So let's rewrite that again. X sub I plus 1 half vxf squared minus vxi squared all over a sub x. Okay, so we can rewrite this. We want to solve for vxf squared. So vxf squared is equal to, let's put the 2 down here, 2ax instead of over there. Okay, so vxf squared is equal to, we're going to multiply everything by 2ax. So we're going to get vxi squared, because this moves to the other side, becomes positive. Multiply everything by 2ax plus 2ax times x sub f minus x sub I. Okay, and this is another equation. Now, if we took acceleration to be 0, then we would see that the velocity doesn't change at all. Vxf squared equals vxi. Okay. So we have these equations. This one's useful. I think this one's useful. These four are definitely useful for solving for different things. And this one might be useful too, right? There's a number of equations that we're going to get that we can use to solve various problems given certain conditions, okay? That's what I'm just basically showing you here, is we're not using any advanced calculus, we're just doing basic algebra, okay? It will behoove the student to actually write down the useful equations for this particular situation. There's a lot of them, and identify which equation might be more useful than another one, rather than trying to rederive the equations they want to use. There's a good chance you're going to make a mistake in deriving the equations, so it's a good idea to memorize them or to have like a little note card with all the equations written down for constant acceleration. Okay, quick quiz 2.6. In figure 2.12, match each Vx minus t graph on the top with the Ax minus t graph on the bottom that best describes the motion. So in figure 2.12, we have 6 graphs. Let me draw them over here. That, and then that, and then that, and then, so this is Vx, 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 and this is t, t, t. This is A, this is B, and this is C. Okay, and then acceleration graph. So we have Ax here, and this is constant increasing acceleration. This is constant but positive acceleration. And this is acceleration that changes over time. So this is, we're going to call this D, E, and F. So what we need to do is, which graph does this one match, right? Okay. Quick quiz. So which graph of acceleration matches this graph of velocity? So the slope of the velocity doesn't change, and it's positive. This one, it starts off at 0, but then the velocity, the acceleration gradually increases. This one, it's positive, and then it reaches a point where it becomes 0. Okay, so match these guys with each other appropriately. All right, so I'm gonna summarize here the analysis model for you. It's a particle under constant acceleration. So we have equation 2.13. The final velocity is equal to the initial velocity plus the acceleration in the x direction times the time. The average velocity is equal to the two velocities added together divided by 2. This is 2.14. 2.15. We have the final position is equal to the initial position plus 1/2 of the initial velocity plus the final velocity times the time, 2.16. This is the one I like. I really like this equation for some reason. I don't know why. T squared, and then 2.17 is Vxf squared is equal to Vxi squared plus 2 times the acceleration in the x direction times the difference in the positions, right? So that is what the equations are. An example of constant acceleration is this. So the change in the velocity vectors is constant, and it's getting bigger or it's getting smaller, and then it'll get bigger, blah, blah, blah. Examples would be a car accelerating at a constant rate along a straight freeway. So you basically get in the car and you hold the gas at a particular level, and the speedometer rises gradually, just at a constant rate. So it goes 5, 10, 15, 20, 25, 30. A dropped object in the absence of air resistance. So if you live in physics land, when you drop an object from the leaning tower of Pisa on the moon, it will accelerate with constant acceleration. And as long as the air resistance is negligible, it doesn't really compare to the other forces involved. It's also true at low velocities on the Earth. Okay, an object on which a constant net force acts, and a charged particle in a uniform electric field. So that's, you're going to learn about chapter 23, what that means. Okay, notice that for each of these equations, some of the variables are present and some of them are not, right? So this one doesn't have the acceleration. This one doesn't have the acceleration. This one is missing what? It's missing the final velocity. This one is missing time. This one doesn't have any time in there, okay? All right, example 2.7, we're gonna land on a carrier. Okay, welcome to the Navy. A jet lands on an aircraft carrier at a speed of 140 miles per hour, which is about 63 meters per second, okay? Question A, what is its acceleration? Okay, if we have constant acceleration and it stops in 2.0 seconds, okay? So it lands on the carrier, it hits an arresting cable, and it rapidly decelerates at constant acceleration until it comes to rest. So we're just considering that portion of time where it hit the cable and it's stopping on the deck. We're not considering any time outside of there, right? Okay, so what is the acceleration if it stops in 2 seconds due to an arresting cable? So we have the time, we have the initial velocity, we have the final velocity is 0, right? 0 miles per hour, right? We have the initial velocity, we have the time. Do we have a distance? All right. Let's see if we can just use these two things. So we know it goes from 140 to 0 in 2 seconds. And we're looking for the acceleration. So we want an equation that has the acceleration. There. This one also has the position. That's not a good one. This one has the acceleration, the two velocities, and the time. So we can solve using this equation. Okay. So we're going to say the acceleration is equal to Vxf minus Vxi. I'm just rewriting that equation, divided by t. So the final is 0 minus 140 miles per hour and dividing it by 2.0 seconds. So it's negative 70 miles per hour per second. Or if you want to use this one, 63 divided by 2, that's going to be 31.5. So 32, because we want to round to 32. So minus 32 meters per second squared. Okay. Pretty easy stuff. You just got to find the right equation and use it. B, if the jet touches down at the final position is 0, initial position is 0, what is the final position, right? So we can use any of these equations as long as there's x of f and x of I. We can use this one. This one's probably the most useful one, I think, because we have, that's going to be 0. That's going to be 0. So let's use that one. The final position is equal to the initial position plus 1/2 of the initial velocity plus the final velocity times the time. So that's going to be, the initial position is 0. The initial velocity is 63 meters per second. The final velocity is 0, and it's 2.0 seconds. Well, those twos cancel, so we just get 63 meters. Okay? Pretty easy. What if, suppose a jet lands on the deck of the aircraft carrier with a speed faster than 63 meters per second, but has the same acceleration due to the cable in part A? How will it change the answer to part B? right? So suppose we landed at a higher velocity, right? Will it, and it's the same acceleration, right? What is the final position going to be? Is it going to be greater than or less than? So if we increase that initial speed, how is the answer going to change? It's going to be proportional. So if he's coming down twice as fast, he's going to need twice as long to finish it. Okay? All right. Example 2.8. Okay. I'm going to bring this page back, by the way, to remember the equations. Car traveling at constant speed of 45 meters per second. 45.0 meters per second. 3 significant figures. Passes a trooper on a motorcycle hidden behind a billboard. 1 second later, after the speeding car passes the billboard, the trooper sets out from the billboard to catch the car, accelerating at a constant rate of 3.00 meters per second squared. How long does it take the trooper to overtake the car? Okay, so we want to know, I guess they want to know how long after. So he takes a speedometer, beep, beep, and then he waits a second, and then he starts driving from rest. So the initial velocity is 0, okay? And he needs to overtake the car. So he needs to pass the car. Okay, so they have a nice little diagram up here. So here is the trooper, and here is the car at TA. Okay, and then he waits a second, so 1 second passes, and now the car is here. The trooper's still here, right? So this is time A, and at time B, the trooper is there, and now the car is at time B. Okay, and then at some point later, at time C, the trooper has passed. So he is whoomp, okay? And I'm just going to put T for that time. Okay, and his acceleration is 3.00 meters per second squared. Okay, and so this car's initial velocity is the same. It doesn't change. He doesn't slow down or speed up. Okay. Okay. So we have these 3 things that we need to consider. Okay. So the position of the car at A, well, that's just 0. At B, that's 1 second times 45 meters per second. So that's just 45.0 meters. And at C is some unknown. So it's going to be 45 plus unknown time times 45 meters per second. Okay. All right. Does that make sense? So that's the position of the car. Okay. And so at time t equals 0, the car is at 0. At time t, 1 second, it's at 45 meters. And at time c, it's at 45 plus the speed that happened after that. We can rewrite this as 45.0 meters per second times 1 plus t. 1 second plus t. Okay. The trooper starts at rest at time b equals 0 and accelerates a sub x equals 3 meters per second away from the origin. So this is a little bit, so he has to cover a distance of this much in that much time, right? So the final position of the trooper is going to be this number here. Okay. The initial position is 0. And he takes a certain amount of time. We're trying to calculate the time. And his acceleration is given, so we know that. The initial velocity, we know that. The final velocity, we don't know that, right? Okay, so let's look at these equations. So we know the positions, initial velocity, we don't know the final velocity. So this looks like the right equation to use. This will solve for time. We don't know the final velocity, so we can't use that. So we can't use any of these other equations. This is the only equation we can use, right? So we say the final position, which is this, equals the initial position, which is 0, plus the initial velocity times the time taken, plus 1/2 the acceleration times time squared. Okay, so this is 0 plus 0 plus 1/2, and we know a sub x. We're looking to solve for t. Okay, so let's put this in for, that's the final position. So we have, I'm going to say this is the Vx car. Vx car times 1 plus t is equal to 1/2 axt squared. We want to solve for t. So let's arrange all these things and move them around. Okay. So we get, let's put all the stuff on one side. So we get 1/2 axt squared minus Vx car t minus Vx car times 1 equals 0. And we can use the quadratic equation to solve for t. So it's minus b plus or minus Vx car plus or minus the square root of 1/2 of a squared. So that's b squared minus 4ac. That's right. So Vx car squared minus 4ac. So it's 2ax times minus, so 2ax, Vx car. Is that correct? Yeah. Divided by 2a. So that's just ax. Okay? And we could plug all these numbers in. Okay? And we're going to end up with 45 meters per second over 3 meters per second squared, plus or minus this stuff. And the answer is going to be 31.0 seconds. Okay? I think I might have done this one wrong. Why didn't we choose t equals 0 as the time at which the car passes the trooper? Well, I guess I did, because I'm not even considering the motion between A and B. I'm only considering the motion between B and C, right? And so it kind of doesn't matter how I did it that way. Okay. That is basically that section. I hope you guys have a good day. Take care. Bye-bye.